During this second module, we are dealing with nuclear physics and its application. And in this 10th video, we will show how a portion of the nuclear binding energy can be transformed into heat by fusion. After having watched this video, you will know the principle of energy release by nuclear fusion. You will know how the stars use fusion to produce the energy and also heavy elements. And you will know the application of this principle to future power plants. Let us return to the spectrum of the binding energy per nucleon as a function of the mass number A. We see that there is a maximum for A equals 60 around iron. For lighter nuclei, the dependence of the binding energy on A is much stronger than for heavier nuclei. Light nuclei are generally less strongly bound, except for the double magic nuclei, like for instance helium-4, and their binding energy increases fast with A. One can therefore use this strong variation of binding energy with respect to the mass number of light nuclei as a source of energy by fusion. The yield of energy per nucleon is greater than what obtained by fission, but the yield per nucleus is smaller because of the lower mass number A. In any case, the natural abundances of light nuclei make this process interesting. In particular, the fusion of light elements is the source of energy in stars. In principle, fusion can occur when two light nuclei come close together enough so that they can merge. But for this to occur, they have to overcome the Coulomb barrier. The maximum potential is reached when the two nuclei just touch. For a mass number of about 8, this maximum potential is of the order of 4 MeV. So a kinetic energy of few MeV can overcome the barrier. One must thus heat nuclei at very high temperatures so that they can overcome the Coulomb barrier. To estimate this temperature, let's say that each nucleus must have a kinetic energy of 2 MeV, which corresponds to a temperature of 10 billion Kelvin. Typical temperature inside the Sun and other stars are of the order of 15 million Kelvin. But the tail of the Maxwell distribution, the Sun spectrum, reaches far enough for fusion to take place. Currently, in the heart of the Sun, every second about 627 million tons of hydrogen fuse and produce about 622 million tons of helium. The difference in mass of 4.3 million tons of hydrogen, which is of the order of the mass of the Giza pyramid, is equivalent to the luminous energy produced, which is about 4 times 10 to the 26 joules. The Sun will still burn for 1 billion years before running out of fuel. Ideal conditions for nuclear fusion prevail within stars. An example is the Sun, which weighs about 10 to the 30 kilograms, mainly in the form of ionized hydrogen. The main source of the Sun energy is the hydrogen combustion, the proton-proton cycle shown in this schematic. The large energy release in the third stage is due to the fact that helium nucleus is doubly magic and extremely tightly bound. In total, a cycle fuses 4 hydrogen nuclei to produce 2 positrons, 2 neutrinos, 2 photons, and 24.68 MeV of kinetic energy. Positron annihilates with ambient electrons and so contribute to the total energy release. Photons can also interact with stellar matter and deposit their energy. Neutrinos escape. Helium produced in the proton-proton cycle can then produce carbon through a double fusion. For the synthesis synthesis of heavy elements in stars, the CNO cycle, also called the carbon cycle, is fundamental. For stars heavier than the Sun, this is even the dominant energy source. Nitrogen and oxygen are produced in this cyclic exothermal reaction. In addition, positrons and photons are emitted in the process. Neutrinos escape from the Sun, often without interacting. Elements up to iron are abundantly cooked inside stars following similar cycles. Even beyond, the chain does not stop. All stable and unstable elements can be produced under favorable conditions. One finds elements up to iron and beyond in cosmic rays from exploding stars in supernovae. Their chemical composition is, however, modified by interaction with the interstellar medium. For example, the lithium-beryllium-boron group is enriched by spallation of heavier nuclei. In general, the abundance of odd nuclei is more important in cosmic rays than inside stars. Our experiment, the Alpha Magnetic Spectrometer, AMS, on the International Space Station, is taking data since several years and is measuring the chemical composition of cosmic rays as a function of their energy with high precision. This will enrich our knowledge on the origin and propagation of cosmic rays. There is a substantial effort to achieve man-made nuclear fusion under controlled conditions. Various fusion processes between deuterium and tritium have been observed in laboratory conditions. The most important one is deuterium plus tritium, which produced helium-4 plus a neutron plus 17.6 MeV of energy. The main difficulty for a fusion reactor is to maintain the fuel long enough at a sufficiently high temperature so that it can penetrate the Coulomb barrier often enough to have a sustained process. One can contain hot plasma in two ways: by magnetic confinement, where the plasma flows in an helical orbit, or by inertial confinement, where electromagnetic energy via lasers or heavy ions is injected into a small area that contains the fuel. ITER, which is the International Thermonuclear Experiment Reactor, is the largest current project with the aim of demonstrating fusion energy production. The reactor is being built in the south of France. In the next two videos, we will take you to visit the experimental tokamak reactor at EPFL Lausanne and the world's oldest working nuclear power plants in Besnau.